Okay, last meeting, this is where we ended. Example problem number 4, where a plug flow reactor is to facilitate a gaseous reaction given the rate law of such a reaction and its composition. So we dealt with the feed that is 50% of A and 50% of the inert. And we ended with this problem. However, it was not fully finished because we had lacked the time then. So I'd like to go back to the start of the problem. Anyhow, the working equation is there already. And all we have to do is write down the needed value for the integral, the definite integral that we are to process. So it was already actually uploaded because it was part of the part 4 of the recordings. But nonetheless, to have continuity, I'd like to start here again. So example 4 talks about a homogeneous gas reaction of A being converted to 3 moles of product R. Now, the operating condition is at 5 atm and 215 degrees Celsius, starting with an initial concentration of 0.0625 mole per liter of A for a feed consisting of 50% A and 50% inert. And it's desired that we will have 80% conversion. So I'd like to go to our solution. I'll go straight to the solution anyway. If you will be listening to the previous slide, since I was not able to cut it, if I will cut it, I will render it again. It will really take time in rendering. So the given I already discussed there. So I'd like to go straight to the solution to this fourth sample problem. Okay, now if you notice in the first 3 sample problems, and that would be this one included, it is always suggested that you start with the performance equation for that particular ideal reactor that is being specified in the problem. In our case, we're given a plug flow reactor. Okay, a plug flow reactor. So its working equation or its performance equation actually is similar to that of the batch reactor, wherein there's a need for us to integrate. So it's only the mixed flow reactor or the CSTR that there's no need for us to do integration. So for our performance equation for this particular reactor, it's CAO integral of dXA over the rate. And of course, we are to integrate this from 0 to whatever degree of conversion is stated in the problem, or it could be also the one that is being required in the problem. So the integral here on the right side of the equation, when multiplied to CAO, will allow you to determine the space-time, or the time it would take for your particular designed reactor, in this case the plug flow reactor, to process 1 reactor volume of feed based on the desired degree of conversion. So this CAO is actually your NAO over VO, the initial volume. So this in itself is also a constant. Now in here, in the rate, we will plug in the rate expression that is given in the problem. So we have 0 to 0.80 because the problem gave us that the desired conversion is 80%. And we have here dXA. And for the rate, we will change it to, it's 10 raised to 1 to negative 2. So that would be 0.01. And that would be CA raised to 0.5. So if you recall, we changed this. We changed this to its expression wherein we already accounted for the epsilon A, or the expansion factor as you call it. So CAO, we have 0 to 0.8 would then be, you can actually place the 0.01 in here before the integral because it's a constant just like CAO, and you can write and you can rewrite the CA into CAO 1 minus XA quantity 1 plus epsilon A XA. The entire expression will be raised to 0.5 because here it's being raised to 0.5. And we can cancel this one. We can cancel the CAO. Can cancel the CAO, leaving the CAO with 0.5 because we only took out 0.5, and this one will go up and this one remains here. So our integral now would be, or rather our expression now would be CAO raised to 0.5 over 0.01. Okay, wait class, I need to admit to. And then this would be the integral from 0 to 0.8. And as I was saying, you will have here 1 plus epsilon A xa raised to 0.5 dxa. And you have here 1 minus xa raised to 0.5. This came from this expression that we have here. This one goes up, this one remains here, and this one cancels with the 0.5 in here, having CAO raised to 0.5 left on the original CAO. So this is our expression now. Now, was anybody able to take down notes last meeting as to what's the value of the epsilon A that we got? Because if there's none, then we really have to recompute the epsilon A. What's the value of epsilon A?
1, miss.
Okay, so it's 1. So this is 1.0. So in this case, we will have a CAO. The CAO that is given in the problem is 0.0625. So this is 0.0625. We'll get the square root of that. We divide this by 0.01. Then we have 0 to 0.8. Then we have 1 plus XA, and you have 1 minus XA. Actually, this is all under the square root sign because of this 0.5, and you will have here the XA. Let me again accept somebody. Okay. Now, so this is your corresponding expression. So if you will evaluate the integral anyway, there won't be any problem with that because you are dealing with a definite integral. The tau value will be right away solved. So what is the tau value that you can solve from this one? So 33.18. Oh, sorry for that. Why did I close it? So this is 33.18. So your CAO is, what's our unit here? Let me check. So what should be the corresponding unit? Seconds. Okay, so that's the tau that the problem is asking. I took a screenshot of our problem, and let me check what do I have here. Find the space-time. So since our rate is in mole per liter per second, then our time would be in seconds. So this is our tau for our sample problem number 4. Okay, so any question for this sample problem before we go to sample problem number 5, the last in the previous set of slides, before we go to the next set? Okay, there's none, so I will stop sharing here. Okay. So what are the key points that we should be learning out of the exercise of having to determine the space-time for a plug flow reactor? So this example demonstrates the design of a plug flow reactor, the determination of the space-time that is. And if you're already given the space-time, then if we are provided with the flow rate, we will know the size of the reactor. In this case, we're not given the volumetric flow rate, but if the problem gave you the volumetric flow rate, the volume will follow because we know that our space-time is the volume divided by the volumetric flow rate. So this is the space-time required to achieve a given objective when the reaction stoichiometry and the reaction rate expressions are known. So in this case, we are already given the rate law because the problem gave it already for us. If not, we'll be the one to determine using the integral analysis or whichever analysis is applicable. Now, this sample problem also demonstrates that the integral involved in the performance equation for a tubular reactor can be evaluated graphically or numerically. Now, this was exactly copied from the conclusion of Levenspiel when he discussed this said sample problem. Before that, this book that we're using is being used by students who does not have the calculator that has the capacity to do integration. So what they do, it's still mano-mano. They solve for the value of the integral using the techniques of integration taught to them and then apply the given limits. Now, in your case, you just simply have to input the given integral and then solve for it. But there's two ways of doing it. You do it graphically, which is very crude, or analytically or numerically. But in your case, the calculator did it for you, as I have mentioned already. Okay, so this one is for those who does not have the calculator to process the integral for them. So if you look intently at your integral, if you're not having the calculator that can process it for you, you still need to recall the appropriate technique of how to handle the given rational radical integral expression. So you still need to think of what Miss Niti probably taught you regarding how do you process a denominator which is a radical. So there's a need for you to rationalize it first before you can determine the answer. But good for us now because everything is almost like instant. Okay, now we go to sample problem number 5. This is still a sample problem on plug flow reactor, but this time we are to determine the volume. The fourth example determine the space-time. Now, the homogeneous gas decomposition of phosphine, which is, of course, a gas, is given here below and proceeds at 1,200 degrees Fahrenheit, provided with this particular rate law. So it's a first order reaction, knowing that the exponent of the concentration term here is understood to be raised to 1. Now, what size of plug flow operating at 1,200 degrees Fahrenheit and 4.6 atm can produce 80% conversion of feed consisting of 4 pound mole of pure phosphine per hour. So let's look into the given now in comparison to the given of the previous sample problem. Now, this is a lot simpler in terms of the given because our given is pure. It doesn't have impurity, so it's all 100% phosphine. So in terms of determining the expansion factor, you need not worry about determining the volume at 100% of the available substance present initially for your reaction to, for your reactor rather to process. I'd like to go to our board and uh, start with the solution of the said problem. So this is already the fifth sample problem. And we are given here a PFR. Okay. Now, in terms of what's given, you are given this stoichiometry, 4 moles of phosphine reacting, or rather decomposing, to 1 mole of P4 and 6 moles of hydrogen gas. All are gaseous in nature. And then we have the temperature that is given in the problem. So it's 1200 degrees Fahrenheit. And the rate law, it's 10 times the concentration of phosphine. So if I will let phosphine be A, it will not, we will just represent it later on by A. So you are asked, so I'd like to write here the required so I can continue the given information down. You're asked for the volume of the PFR, the operating pressure is 4.6 atm. And what else? 80% conversion is desired. And you have a feed consisting of 4 pound mole per hour of phosphine. So I'd like to have here FAO, and you'll have here FA. So your FAO is the molar feed rate. So as a review, it's molar feed rate, and it's given to be 4 pound mole per hour. So this is all A. So 100% pure A. So that's it, everything there. You have a homogeneous gas decomposition with the provided stoichiometry proceeding at 1200 degrees Fahrenheit and 4.6 atm with a provided rate law of 10C sub A, where A is pH 3 or phosphine, and it's desired that you should have 80% conversion of a feed consisting of 4 pound mole per hour of phosphine. So this is our set of given information. Now we go to the required. Rather the solution, because we already identified the required information. So again, we start with the working equation for the PFR. What's the working equation for the PFR? Anybody? What's the working equation for the PFR? We just discussed it a few minutes ago. That would be T CAO, the integral from 0 to XA of dXA over the rate. Okay, this is our performance equation. But since we have a gaseous reactor or reaction, we need to determine the expansion factor as suggested, because we might forget about that we have an expansion factor to consider. We have a pure gaseous reaction starting with phosphine, 100% phosphine. So in determining the expansion factor, all we have to do is look at the stoichiometry. So get the sum of the coefficients of the product, subtract from it the coefficient of the reactant over the coefficient of the reactant. So in that case, we have 7 minus 4 over 4. Now you have 3/4. So your epsilon A is equal to 0.75. Okay. This is in cases wherein we have a pure feed. Now, checking on what is provided, we have FAO. So we're not given BO, but rather we have FAO. So this CAO is, or initial concentration, can be expressed in terms of what? By the way, in terms of the plug flow reactor, can this be replaced by an FAO expression? This one, the CaO. Anyone? What is this relationship here? CaO, VO. What is this equal to? That's your, Sarah is saying FAO over VO. Very good, Sarah. So this is your relationship actually of CaO-VO relating it to FAO. So when Sarah suggested that CaO can be expressed in terms of FAO, then you can have CaO equal to FAO over V sub O. Okay, now that is in the case of the tau. Now let's go back to what we are provided. So you are given the, you are required for the volume. Okay, now let's go back. If it's the volume that is being required, remember that this tau is also V over V sub O. So I'd like to write here V over V sub O equal to CaO integral from 0 to XA dxa over the rate. Now, since the problem is asking for this, you can transfer this one here and there's no need for you to express the CaO in terms of what is provided in the problem. So actually, the problem is asking for the volume, not asking for the space-time. So since it's not asking for the space-time, then as well, we might as well express the space-time here in terms of volume and see what would the corresponding expression be resulting from it. So if I will have an integral that will be solving for volume, I will have something like this, which will not require me anymore to express the CaO in terms of what I'm provided with, which is the molar feed rate. If volume is not the one that is being asked, then there's a need for you to use this one. But since volume is the one that is being asked, not the space-time, then we can rewrite it in this expression. But nonetheless, this one is correct. Okay? Let me just admit. Okay, now, your CaO-VO as written here is equal to FAO. So then now we have the required or the provided rather information. So this is 0 to XA and we have dXA over the rate. Now I have a generic expression here and I can substitute the 0.75 epsilon A which will be appearing in the rate expression in the denominator of our given integral. So volume would be equal to, I can now substitute what is provided in the problem in terms of FAO, and our FAO is 4 pound-mole per hour. So this is 4. Then I will have the integral 0 to, so your degree of conversion is 0.8. We'll place here the differential of the conversion. And just like what we did in the fourth example, we will use the rate expression that is provided here, 10 C sub A, okay, for ease of writing. So we have 10 C sub A. Now, this C sub A have to be expressed in terms of epsilon A and conversion. So I will have here 4, 0 to 0.8. Just take note of the set of units there. Do you have dxa? This 10 I can place here. And I will have here CaO just the same as what we have done in the fourth sample problem. Okay. Now this is a 0.4. This one goes up. So you have 1. And we have determined epsilon A to be 0.75 a while ago. So this is XA. So this one goes up. What we have here in the denominator is CaO, which we do not have. But what we have here is the temperature and the pressure. So we can actually solve for it later. So I will just place here This CaO being a constant, I'll place here so that I will only deal with the expression that I have here, 1 minus XA. So you can evaluate this integral and multiply the corresponding answer with the 0.4 CaO. So this is your V. This could be your first equation. As for CaO, so we go back to the main problem without having a CaO. So we have already derived the formula in determining the CaO in terms of PaO. So PaO, what do I place here? It's N over B. It's PV over nRT. So what do we do? PaO. CaO is PaO over RT, right? Now, your PaO is understood to be the given pressure given in the problem. So we started with this particular pressure of 4.6 atm. Now, since you started with 100% pure phosphine, then this 4.6 pressure is all due to phosphine. So if you did not start with a 100% pure phosphine feed, then this particular pressure should be only multiplied to that amount of percentage amount of phosphine that is present in the feed. But in this case, it's all 100%, so your PaO will be 4.6. So you multiply here, or rather substitute the 4.6 atm here. What's the appropriate R that you will use in this case? You're given ATM. So that would be your 0.08206. Is that right? This is ATM, liter per mole, Kelvin. Then you cancel the ATM here. So you have to multiply the denominator with the temperature in Kelvin. That is the case. So now, since the temperature is in Fahrenheit, you can convert the Fahrenheit to centigrade or Celsius, then convert it to Kelvin. That way you can find the appropriate, you can have the appropriate unit, which is Kelvin, which will cancel out in here. Can you please solve for the equivalent temperature in Kelvin of 1200 degrees Fahrenheit? That way you will have a CaO value, which is already in mole per liter, which you can substitute to our previous equation. This is our previous equation here, equation 1. Please convert 1200 degrees Fahrenheit to Kelvin. Okay, so thank you, Mika and Jabi May. It's 922.03. This is still Celsius. Kelvin na ini siguro. Kelvin na. Okay, so Kelvin na siya. So this is already in Kelvin. So we get to cancel. And the corresponding amount of the initial concentration of phosphine is what's their initial concentration of phosphine? Can I have other volunteers? So I have here Jabi May, it's 0.0608. Okay. So I would like to encourage the rest to also participate in the discussion. So it's the same people that's providing with the values that I'm asking for. Anyway, it's an exercise for you also. So now you know the CaO, you go back to equation 1. So substitute CaO to equation 1. Your equation 1 requires you to solve for the volume. And that would be 0.4 divided by the CAO. So 0.4 divided by 0.0608, and the corresponding value of the integral that you will be getting if you will let Mr. Casio do it for you. So just place encode the expression for the integral with the appropriate limits 0 to 0.8, and less than a minute you will have an answer for the said integral. What's the integral expression? So you will have a volume here which is in liters. Okay, what's your integral? I'm referring to this integral here. What's the value? Aliana. So thank you, Aliana. So 14.5, Antoinette and the rest. Giselle, 14.58. 14.58 liters. So this is our volume. Okay, for our plug flow reactor. So I think the 5 sample problems would suffice for the necessary intro to the design of single reactors, facilitating single reactions. Now, the ease in using the performance equations that we have derived for the 3 ideal reactors came easy because we are already provided with the rate law. So it is a given class that when the rate law is not provided, then you are to apply what we have discussed the entire midterm regarding interpretation of batch reactor data. That way we will have the appropriate rate law to plug in to our performance equation. So there's somebody chatting here. Miss Galing, pound mole per hour. Ang 0.4, Miss. Wait, let me check. Pound mole per hour. Thank you, Joshua. The 0.4, okay, that I missed. So it's 4 pound mole per hour. Wait, this is pound mole per hour. And the one that we use for the R is in mole. So you just convert this one. So we will have a different, this is mole, or we can do conversion here. You can have, this is understood to be gram mole. So we have 454 mole per pound mole. Please check if my conversion is correct. Okay, it has been a while since I used this particular conversion. So you will have pound mole per liter. So then this would even be smaller. So our answer here should be divided by also where did we place the answer? The 0.06 is in here. So our answer should be multiplied by 454 because this one is in gram mole. So it should be multiplied by 454. So there's a need for you to place in here the given integral, and there's this conversion here of 454. So in liters, what's our answer then? All you have to do is multiply the 14.58 by 454. 6 to 20. Almost the same. So we will use the 6,620. Or 6, whichever of the two. I think it's in the decimal, 6,620. Okay? Or you can have 6,619.32. But more or less, this is the volume in liters. Quite big. 6,620 liters. That's the volume of our PFR. Thank you, Joshua, for checking that our units agree. Okay, so that's one thing that you also should be very careful in terms of the units that are provided in the problem. Okay, any question here so far? So this is our answer now for the fifth sample problem. Now, if there aren't any question here, I'll go back to our slide. And this is our last sample problem. And the last part in the slide is talking about the holding time and the space time. So for flow reactors, I'm referring to constantly stirred tank reactors and tubular reactors. We're using space time. In batch reactor, we're using holding time or residence time. And we normally represent it with a T or a T with a bar. That would be your holding time. The space time is represented by the tau. Now let's compare the two. So when you speak of the holding time, that would be the mean residence time for the batch reactor. This is also referred to as the time of reaction for your particular mixture that you place inside your batch reactor that will acquire a certain degree of conversion as stated in the problem. Whereas the space-time is the time required to process one reactor volume of feed for your flow reactors, of course, at specified conditions. So the language of the space-time is used for flow systems, whereas the language holding time or residence time or reaction time is used for the batch reactor. Now, the holding time, there's a note here, and the space-time is the same for constant density system. What does this mean? So if I have a plug flow reactor and I will use the term holding time, it's okay as long as the reaction that is happening in my batch or in my tubular reactor is constant density, meaning volume is not varying. But if the volume is varying, then it has to be space-time that I should be using. But it is always advised, class, that we will use the term space-time for flow reactors. And we will use residence time or holding time, but what is usually used is residence time for batch reactor. Now, Levenspiel gave us a summary of formula for the performance equations for nth order kinetics, meaning for any order of reaction as long as it's either 0, 1, 2, or nth order. Here you have a generic representation. For the plug flow and for the mixed flow, it's a summarized set of formula written in a table, and you can also see them as well in the soft copy of your Levenspiel, the third edition. So for a zero order plug flow reactor, this is your performance equation already pre-derived for you for first order, for second order. Notice that the epsilon A is appearing because we do not know that for a plug flow reactor, we're not certain that at all times epsilon A will be 0. Should it have a value, then all you have to do is plug in this particular epsilon A that you predetermined when you start solving the problem. Now, for any nth order reaction, class, it's suggested that you work on your given integral. You work on the integral if it's already 0.5 or 0.33 or negative 1.5 or something like that. So you have to work it out. But you have something ready already to use for 0, 1, and 2 orders for plug flow reactors. Now for mixed flow, you also have it here. And for any nth order reaction, since mixed flow reactors does not have any integration, you have this as your ready-made formula. So whether your n is positive or negative, a whole number or not, then this one will be working for you for your mixed flow reactor. For a first order reversible reaction, you have it in here. For the plug flow, you have something here that is derived as long as you don't have any initial product present. Okay, initial concentration of your product is 0 in this case. If you have an initial amount of R, then this formula will not be working for you. Same thing for the mixed flow reactor, reversible first order reaction. So as for the general expression, you know this already. So this is how we solve for the tau for plug flow, and this is how we solve for the tau for the mixed flow reactor. If asked what is the residence time for a batch reactor, it's the same thing as the plug flow reactor. You just have to change the tau to T. Because residence time, you're using residence time or holding time for your plug flow reactor. So ready-made formulas already summarized for you. Okay? So any question for this set of slides before we go to the last one, which will comprise the last 3 topics that were written in the outline, the course outline that was also published in Canvas for you. Have any question here? Okay, so no question here. I will stop. I will share a new set of slide. Yes, this one. Let me see. Okay, so this is a set of slides that will cover the last 3 topics. So I did not anymore break it down per topic because anyway, that's the set of slides is very short. Very short, however, one sample problem will entail time in solving. So I already placed in here everything that we will be needing for module number 4 in this last set of slides for module 4. Okay, now for this particular set of slides, we'll be first talking about comparing sizes for flow reactors, meaning what will require a bigger reactor size in terms of conversion, or which of the two will have a greater degree of conversion given the size of the reactor. So we'll be talking about that in size comparison. So like if I will be requiring a bigger volume for a CSTR given the same set of conversion as the PFR, then if I need to process a bigger bulk of liquid or rather feed, then which of the two I'll be using. So that's the purpose or the significance of being able to compare sizes for the flow reactors. Now, however, there is a downside on that. So if a CSTR can process a bigger volume of feed, what about the degree of conversion for such a bigger volume of feed to be processed? So I will not say it now, but later on you will see that an advantage of one will be a disadvantage of another, and a disadvantage of another will be the advantage of one in terms of comparison, comparing the two flow reactors only. So we're not talking about batch reactor here. We'll be just simply comparing the CSTR and the PFR. Then after being able to compare the sizes of reactors and then their conversions, we'll be talking about multiple reactor systems. So in here, we may be talking about similar reactors in your system of reactors. So we can have all CSTRs, or we can have it combined with CSTR, or we can have a combined multiple reactor system like a CSTR and a PFR. Something like that, a CSTR, then a PFR, and another CSTR in the end. So it depends on the design for your particular multiple reactor system. That we will also be talking about here. And we will incorporate, of course, the performance equations that you have learned in the previous set of slides. And then we will have the design of recycle flow reactors. So what is happening when we recycle a portion of, let's say, the product stream of a particular reactor and use it as a feed, either on that same reactor or on the succeeding reactor, part in the succeeding reactor and part on the same reactor. So we will be talking about that in here in the design of recycle reactors. So this will be the last 3 topics for module 4, which I placed in this slide. Okay, we compare sizes, We design multiple reactor systems, and we tackle problems concerning recycle flow reactors. Now, it begins here with the factors to consider in designing a reactor. So generic, it could be a batch reactor, it could be a semi-batch reactor, or it could be a flow reactor. Now, there are 8 factors to consider in designing a reactor, and you are seeing the first 5 of those factors in here. So number 1 is what reaction type is it to facilitate? Now, is it going to facilitate a parallel reaction, a reversible reaction, an irreversible reaction, a series reaction? So that should be something to be considered. Now, the plant scale of production, is it small scale or large scale? Or is the feed that large that it will require a bigger volume to be processed at a particular time? So we need to look into this also. The plant scale of production. Then the cost of equipment and operation. So what will be compensated for the cost of equipment in terms of initial cost of its design is the operation, because sometimes you will entail a lot of cost. There's a lot of cost initially, but during operation the cost is not that much. However, there's also a design wherein you will not entail a lot of cost in the beginning, but in terms of operation or operational cost, that's where it's going to hurt. So it's a balance of these two that we're looking into. Then safety of operation, and the stability and the flexibility of operation. Flexibility in the sense that we don't only limit your reactor or your reactor system for a particular type of reaction only, meaning that your particular reactor or reactor system can also handle a different type of reaction or different types of reactions, not only limited to one type. So that's flexibility of having it operated. So this is the first 5. The last 3 you have in here, we have to look into the life of the equipment. So equipment life expectancy based on how it is operated, the length of time that the product is expected to be manufactured, how long will you be able to produce the product with the given quantity, of course, and the ease of convertibility of equipment to modified operating conditions. This means that initially, probably your reactor will not need a coolant or a cooling liquid or a heating medium for the reactor that is to be placed into it. But there are reactors that will require a coolant or a heating medium for the reaction to proceed. So in that case, your reactor can be initially jacketed, but if your reaction does not need, this is an example, does not need for it to have a coolant or a heating fluid, then there's no need for any fluid in the jacket of your reactor. But once there's a need already, then have a coolant or a heating fluid in that particular jacket for your reactor. So that refers to the convertibility of the equipment to modified operating conditions or to new and different processes. So not only very limited to a particular process, because that would mean also cost in the end. So these 8 are things to consider when we design a reactor or when we design, of course, a reactor system that is comprising already of several reactors, either of the same kind or of different kinds. Now, that might be overwhelming upon hearing it, but don't be overwhelmed, because we are all neophytes in this, and specifically I'm also only teaching based on theories that I have learned in the book and that I have read also. It's different when you have already experienced. Now, this is number 1 in selecting a reasonable reactor design. So nothing beats experience. Even all the books you have read, but in the actual, there are things that needs to be modified in the actual operation, in the actual condition, or in the actual processing of your feed. There's a lot of things to consider that later on will really require you to be really exposed to what we call industry, to the industry that really requires the said reactor. So experience is number 1. After experience, of course, you will have this. You cannot have a good engineering judgment if you lack experience. And what we do now, we just compute based on what the principles and the theories that we have read in the book. Sound knowledge of the characteristics of the various reactor systems. Sound knowledge, this could be read, but reading is not enough, will not suffice. So you need still experience. There's no bullet here. This one is a continuation of this one. And the last is we did not forget economics. So monetary side, we have to consider economics also. Now, this is not included in Rainville, in Levenspiel rather, but I think it's very important that sustainability has to be considered also in reactor design. It's not just you already have the experience, you have the very good judgment based on your experience, you have a sound knowledge of the characteristics of the behavior of your chemical system and even your system of reactors, but only considering economics will, of course, in the end, not profit humanity. There has to be sustainability. Okay, imo design pero it limits the enjoyment of the future generation for uh, the degree of enjoyment that we are currently enjoying. So sustainability or the impact of the design of your reactor or reactor system to the environment has to be considered. It's not written here then because if you look at the copyright of Levenspiel, I think it was 2000, more than 20 years old na ina siya, ang third edition. Even the second edition, which this one is based on, is as old as 1970s, wherein some all of you are not yet born. Okay, so they are not yet having that much problem in terms of sustainability or the impact to the environment of all systems, not just reactor systems. So we have to add here sustainability to a reasonable reactor design, not just the four that is stated here. Now we'll end here. I will continue after 10 minutes in the next link that I have provided in our GC. Okay? So I will be checked there. So we will just transfer. You have a 10-minute break after this. Bye for now, class.